expressions and equations and solutions to equations, the next thing that we want to do is figure out how we can actually find the solutions to an equation that we're interested in. So for example, remember our problem that we had last time. So let's suppose that we want to throw a party and the cost of that party is going to be 200 plus 32p, where p is the number of people involved. Or invited, I should say. And let's suppose further that we've got a total budget for the party of $1,800. And we want to know how many people can we invite? Now, we'll invite the maximum number of people when the total cost of the party equals the total budget. We want to use up the whole budget, invite as many people as we can. So in other words, we can express the question here as what's the solution to the equation 200 plus 32p equals 1,800. What value of p will make the cost of the party equal the budget for the party? And that's the question that we would like to answer. What value of p can we plug in here? Now, of course, you could try guessing a bunch. You could try plugging in a bunch of different values for p. You could say, well, what if we invite 10 people? Well, if you invite 10 people, then the cost of the party is $520, so we could invite more. So, well, then what about 20 people? What about 30 people? And so on and so forth. And you could try a bunch there. Now, this process isn't very good for a couple of reasons. First of all, it's time-consuming. You've got to guess and check a whole bunch of different possible values for p. Most of them won't work. And second, this won't give you the answer for equations where the value of the variable happens to be a fraction or something else that's not a whole number. You won't ever be sure that you've gotten all of the possible numbers that you could plug in for p. And there's an additional problem where going through that method will only find you one solution and won't necessarily tell you that it's the only solution involved. So we need a more general strategy here. And what we're going to take advantage of is what I call the general algebraic principle. This is the idea that we're going to take advantage of throughout all of algebra. And it's the following. In general, you can do the same thing to both sides of an equation without changing its solution set. Now, this is a very general and pretty vague statement here, but it captures the idea, and we'll see here in just a second some precise examples of what we mean by this general algebraic principle. But I want to introduce this right away because this is really something that we want to keep in mind that we're going to take advantage of throughout the entire course. In general, if I've got an equation and I want to get another equation that has the same solution set, I can, as long as I change both sides of the equation in the same way, as long as I balance things out. So as I said, this is pretty vague, so let me make this much more explicit with an example of a few things that we're allowed to do to both sides of an equation. So I'm going to write this down as a theorem. Now, a theorem is a mathematical fact. It's something that you can always rely on. It's just true. And let's write it down this way. I'll write it as capital A and capital B are expressions. So capital A, capital B, they could be complex. They could have lots of numbers, lots of variables in them. I just want to use symbols to stand for these expressions. And if they are expressions, the solution set for the equation A equals B is the same as the solution set of each of the following. I'm going to write down 4 more equations that each have the same solution set as the equation A equals B. So, A equals B has the same solution set as the equation A plus C equals B plus C, where here C is again any expression. So this first part here is saying that if I add the same thing to both sides of an equation, I don't change the solution set. The solution set for the new equation, A plus C equals B plus C, is exactly the same as the solution set to the original. And the same is true if I subtract. And the same is true if I multiply, although here I can't allow C to be equal to 0. And the same is true if I divide both sides by C, as long as C is not equal to 0. So this is saying that we can add, subtract, multiply, or divide 2 sides of an equation by anything we want, other than 0, and get a new equation which has the same solution set as the original. Now, this gives us a lot of freedom. It means that we, as people working on math problems, have a lot of power, a lot of options for how we can work with this. And so a lot of what we're going to be doing is not just grinding out algorithms, but it's going to be practicing looking at a problem and saying, all right, well, which of these facts can I use? How can I be clever in choosing what I want to add and what I want to subtract to both sides of an equation in order to make my problem simpler? So let's do this. Let's use this theorem to solve the problem that we had on the previous slide with the party. So let's find the solutions to 200 plus 32p equals 1800. Now we'll go through this a little slowly, but we'll see in a second that we can do things a little bit more compactly using some efficient notation. So we have this equation, 200 plus 32p equals 1800, and I'm going to give this equation a name. I'm going to call this equation star. Now, I'm going to use the theorem to change this equation. I want to add or subtract something, in this case, from both sides of the equation in order to give me a new one, which is simpler. The whole point of this process is going to be simplifying this equation, or getting new equations which are simpler, and in particular, our goal is going to be to get the variable p by itself. We'll see that once we get the variable p by itself, the equation that we get once we get there has a very, very simple solution set that we'll be able to work with. So, by the theorem, the first thing I'm going to do is going to say that star has the same solution set as the following. I'm going to take the same equation, but I'm going to subtract 200 from both sides of the equation. Now, I could have subtracted anything here or added anything. I could have subtracted 10 or 100 or 1,000,000, but I wanted to make the problem simpler. And you'll notice that when I subtract 200, then on the left-hand side of this equation, I now have two terms which are going to cancel out. So the 200 and the negative 200, these two are going to cancel out with each other. And when we simplify this equation, or rather simplify the two sides of this equation, when I have 200 plus 32p minus 200, the 200 and the negative 200 will cancel out, and the left-hand side of this equation just becomes 32p. And the right-hand side, well, that's just 1800 minus 200 is 1600. I'm going to give this equation the name double star. So now, by the theorem that we have, equation star and equation double star have the same solution, or have the same solution set, I should say. And that's good. If we knew all the values of p that would make this equation double star true, then that would be the same as all the values of p that make the original equation true. Now, we might be able to think through this and figure it out, but we want to go further. Let's go ahead and use the theorem again. Let's keep doing algebra to simplify our life. Our goal is generally to reduce our equations to something where the solution set is obvious, completely obvious. Really, algebra is about turning complicated problems into problems that are very, very simple. So we're not simple enough. We want to go further. So now I want to think, how can I get the left-hand side of this equation even simpler? How can I get rid of this 32 in particular? So here we use another strategy when solving equations. We want to get this p by itself. We want to get the variable by itself. So we can ask, what's happening to the p right now? Right now, the p is being multiplied by the number 32. That's just what's happening to it on the left-hand side of the equation. And so we can ask, all right, well, how would one undo that? What's the opposite of multiplying by 32? And the opposite of multiplying by 32 is dividing by 32. And so that's what we're going to do to both sides of the equation. Again, by the theorem, doing that is going to give us a new equation with the same solution set as double star. So we're going to divide both sides by 32. And so what we'll get when that happens is we'll get 32p divided by 32 equals 1600 divided by 32. And once again, I want to emphasize that we could have multiplied or divided by any number we want other than 0. And we're choosing 32 because we believe it's going to simplify the equation. It's going to get us closer to having the variable by itself. Now, once we do this, we want to simplify again. And now we have 32 over 32 on the left-hand side. You've got a 32 in the numerator and a 32 in the denominator, and those are going to cancel out. If I multiply by 32 and divide by 32, those two operations undo each other. And so they can both go away, and in fact, if I take p, multiply by 32, divide by 32, I'm just going to be left with p behind. So when we divided the left-hand side by 32, we got just the variable p, And on the right-hand side, you've got 1600 divided by 32. That turns out to be 50. I'm going to give this equation the name triple star. So now we have that double star and triple star have the same solution because we used this theorem again. We divided both sides by the same number. But we also knew from the beginning, from our first step, that single star, the equation single star and double star have the same solution. So if single star and double star have the same solution, and double star and triple star have the same solution, that means that therefore single star and triple star have the same solution. And the reason why this is helpful for us is that the equation triple star is a very simple equation. It's the equation P equals 50. And if I want to know what the solution to that equation is, I ask myself, what number could I plug in for P? What real number value could P take in order to make this equation true? Well, one of the basic properties of real numbers is that a number is only equal to itself. And so the only number you could plug in for P in triple star that would make the equation true is 50. 50 is the only solution to triple star, and therefore 50 is the only solution to the original equation. So our answer to the original problem, find solutions to 200 plus 32p equals 1800, is that 50 is the only solution. And we did that by taking this equation and using the general algebraic principle, using the theorem that we had, twice in order to simplify this equation down a couple of times in order to get to an equation where the solution to the final equation is totally obvious. And this is the strategy that we're going to use in a lot of problems. So, what does this mean in the context of our original problem? Remember that this equation came from our problem where we wanted to find out how many people we could invite to our party in order to use up our whole budget, and now we have our answer. We can invite 50 people to the party. That will use up the entire budget with none left over. So that's the answer to the party problem. So let's look at another example, and I want to show you some simpler notation. This process that we're going to use of adding the same thing to both sides or dividing this both sides by the same thing is something we're going to use over and over and over again. And so I want us to have a more efficient way of doing it. So let's look at another problem. Let's say we want to find the solutions to the equation 4x plus 15 equals 2x plus 1. Now this equation is a little bit more complicated than the equation that we had to begin with. And that's because we have two terms here with variables in them. We've got an x variable both on the left-hand side of the equation and on the right-hand side of the equation. And what that's going to mean for us is we're going to need to take about one more step to solve this problem than we did for the previous one. But that's all right. That's all right. We can still do this. So let's go ahead and start working it out. We've got 4x plus 15 equals 2x plus 1. So what I'm going to try to do is to get the x's by themselves. I want to get just x on one side of the equation, just a number on the other side like we did last time. If we can get there, then the solution will be obvious. So what I'm going to do is, first of all, subtract something from both sides of the equation, but now I'm going to subtract 2x from both sides. Remember that we're allowed to add and subtract not just numbers, but expressions. So we're allowed to subtract 2x from both sides of this equation. And I want to notate that this way. I'm going to write a minus 2x beneath the two sides of the equation. And in fact, I've even aligned them so that the minus 2x that I'm subtracting lies below the corresponding term on the left-hand side and the right-hand side. This allows me to make sure that I'm doing the same thing to both sides, because I need to make sure that whatever I subtract on one side of the equation, I'm doing exactly the same thing on the other. So notice that I've got the 2x on the minus 2x on the left, the minus 2x on the right. They're on opposite sides of the equal sign. And so that means that I am, in fact, doing the same thing to both sides of the equation. I'm subtracting 2x in both cases. Now let's see what that looks like once we do that next. We've got 4x plus 15 minus 2x. Now 4x and 2x are like terms, so they can combine. And 4x minus 2x will have an x in it, and that to get the coefficient, we take 4 minus the 2 to get 2. So 4x minus 2x is 2x. Nothing changed about the 15. And on the right-hand side of this equation, we have 2x minus 2x. Well, that's just 0. And so we don't have to write that term at all. We've got 0 plus 1 is 1. So notice that even in this first step, I've simplified the equation. Before, the equation had two terms on each side, and it had an x term on the left and an x term on the right. And after doing one step of this process, I now just have a single x term, the 2x, and a couple of constant terms. So we've made one step towards simplifying things. Let's keep going. Well, next I still want to get this x by itself, so I'm going to take care of this 15 here. So to get rid of a 15, I can subtract 15 from both sides. Because I'm doing the same thing to both sides, then I'm going to get an equation which has the same solution set. Now, 2x plus 15 minus 15 is just 2x, because the 15 and minus 15 cancel out. And then we get 1 minus 15, and 1 minus 15 is negative 14. We're almost there. We just need to do one last thing to get x by itself. X is currently being multiplied by 2, so we can divide both sides by 2. The 2 being multiplied by the x and being divided are going to cancel out, and our final equation is going to be x equals negative 7. Now the solution to x equals negative 7 is just negative 7. Once we get down to variable equals a number, the solution is obvious. The solution set is obvious. The solution set is simply the set containing negative 7. And because we've done the same thing to both sides all the way down, same thing to both sides of the equation all the way down, the solution set to this final equation, x equals negative 7, is the same as the solution set to the original problem, 4x plus 15 equals 2x plus 1. So the answer to the problem is x equals -7. Or just -7, or the solution set being the set containing -7. -7 is the solution to this equation. So this is the general idea that we're going to use to solve equations. Now, just using theorem 1 doesn't work for, just using the theorem that we had doesn't work for all equations. We can write down equations where we need something more than just the theorem that we have to work with. We can't always get by just on multiplying, dividing, adding, and subtracting expressions from both sides. However, there are a lot of equations that we can handle just that way. And so next we're going to be talking about a couple of kinds of equations where we can solve them all the time just by using the theorem from this section.